All right, welcome everybody. I'd like to just remind everyone to keep their microphones muted during the workshop. Thank you very much. We have a full house today, so for the respect of everyone's time, we're going to go ahead and get started. My name is Megan Martell. I will be introducing the speaker and also monitoring the Q&A. Today we have William Fatigante as the speaker. He is an applications scientist within the Applied Markets Division here at Bruker, concentrating on DART-related applications. He received his Master's of Science from the Illinois State University, where he focused on applying ambient mass spec methods for forensic evidence screening and confirmation. Being with Bruker now for 2 years, William has learned the ins and outs of DART-MS and its potential to provide a rapid screening solution to the challenging world of seized drug analysis. And we're thrilled to have him here today for our 1-hour workshop. And just another reminder, if you have any questions, please feel free to throw them in the chat and we will go over them at the Q&A. And without further ado, I'll hand the microphone over to William.
Great. Thanks, Megan. Hello and good afternoon or good morning, depending on where you're at. Again, my name is William. I'm an application scientist with Bruker's Applied Mass Spec Division. I'm sure you all, like me, have been enjoying this week's topics and discussions. So with that being said, I'm excited to share with you all some of our mass spec technology for forensic drug analysis. So here, just a quick overview of today's workshop. We're first going to be talking about some of the problems that the forensic community has been experiencing, and then followed by an introduction to DART ionization and some high-resolution mass spec systems that we offer. From there, we'll discuss targeted DART-MS workflows for with some examples along the way. Then we're going to shift the discussion to trapped ion mobility spectrometry and the benefits that it can bring to the table. And then lastly, I have some non-targeted analysis examples with authentic samples of interest. And then we're going to wrap up this workshop with just kind of quick summary and overview, and then some time for a Q&A session at the end. So before we get started, I wanted to briefly discuss some of the issues experienced in the forensic evidence analysis. So it was reported back in 2019 that roughly 1/3 of total forensic examination requests were that of seized drug analysis. That same report from the National Forensic Laboratory Information Systems, their drug survey of crime lab drug chemistry sections, stated that on average, laboratories were seeing about a 60-day turnaround time with about an 1,800 drug cases within their backlog. So another study performed by the Alabama Department of Forensics found that out of the 120 analysis surveyed, that just over half were of a single analyte, meaning that the other half contained 2 or more analytes present within each sample. This study kind of clearly demonstrates the necessity to be able to screen for multiple analytes at a time. So what does this tell us? This tells us that the common challenges for labs can stem from, just the overall lab testing backlogs, the sample complexity, and the ever-growing list of novel psychoactive substance developments and their derivatives. So a potential aid for this can come from direct analysis in real-time mass spectrometry. There have already been numerous publications demonstrating both its versatility in handling various samples of forensic interest and its ability to meet the high throughput demands that labs require. So here we have a direct analysis of real-time ionization source, or DART. And for the majority of today's workshop, we're going to be talking about its coupling to our high-resolution mass spectrometers, both our quadruple time-of-flight systems and trapped ion mobility spectrometers, and its ability to give kind of a near instantaneous determination of sample composition. So in its simplest terms, DART is a technology that uses heated ionized inert gas to complete thermal desorption and ionization of chemicals for analysis by mass spectrometry. So your sample does not have to be in solution. You can just position a small fraction of the sample into the ionization region and can generate ions off the surface. So this is providing one of DART's biggest appeals, being that sample preparation is non-existent or minimal in most cases. So before going any further, I wanted to take a moment and talk about how the ionization process works. So here we have a DART source, kind of a cutaway image shown and depicting its major components. So we're going to start by taking an inert gas that flows through the back of the source. This is commonly going to be helium as the ionization gas, but nitrogen could be used as well. The gas is going to pass a high voltage needle. An electrical discharge is going to be used to create a plasma containing ions, electrons, and most importantly, the metastables. From there, it's going to pass through a ceramic heater. This heat is going to aid in the desorption of the sample from the surface and help with the ionization. But before exiting the source to meet the sample in the open air, this heated ionized gas is going to pass through a small grid, which we can apply a voltage across. So this voltage is going to help prevent any ion-electron recombination and act as an electron source for negative ion formation. So finally, ionization occurs actually out in the open air in front of the atmospheric pressure inlet of the mass spectrometer. So from that ionization region, the gases are drawn into the mass spec through the API to be analyzed. So what does sampling with DART actually look like? So there's kind of two overall types of sampling with DART. We have manual or automated. With manual, think, directly inserting and ionizing a pill or a powder into the ionization region right in front of the mass spec. This is a common practice in the field of forensics for quick and qualitative analysis. So here we have a picture of a tablet just being held with a pair of tweezers and put right between the DART ion source and the ceramic inlet of the mass spec. And then here we have a glass capillary, lightly touching some of this white powder, and again, being introduced into that ionization region. So now with automated sampling, we can actually use a linear rail to move the sample into the ionization region and also have the option for multiple samples to be analyzed at once. So here what we see is kind of our most popular automated sampler, the quick strip module. So this can introduce up to 12 samples at a time. So the user is actually going to deposit their sample, either liquid or sometimes a powder, onto this stainless steel mesh. So then the automated rail is then going to move this mesh into that open air sample region for ionization. So we even have higher throughput options available. So it's similar with a stainless steel mesh. However, it's going to be in a 96 or 384 sample plate format. So giving you that option for a high throughput analysis. So here at Bruker, we offer 3 different quadruple time of flight mass spectrometers. So each is going to offer the same ion optic systems, with the only difference being, as you can probably clearly see, the difference in TOF lengths. So meaning that we have our compact, which offers 30,000 of full sensitivity resolution, or we have kind of the Maxis 2, which offers our highest resolution of 80,000 resolution. We also have kind of a Goldilocks of the 3, the Impact 2, still offering you 60,000 resolving power. And of course, we do have our line of timsTOF mass spectrometers, which we'll be focusing on later in the presentation. So kind of for this first chapter here, we're going to be using the Impact 2 quadruple time of flight. So again, we have comprehensive screening and quantitation for complex analytical challenges, while offering full sensitivity resolution. So there's no compromise between resolution, sensitivity, and dynamic range. And again, as we'll see, it's going to offer you the flexibility. So we're going to be able to switch in minutes between GC-APCI, UHPLC, and even DART. All right, so for the first chapter of this workshop, we're going to be talking about targeted workflows and screening and identification with DART. So now that we talked about the hardware, let's see how we can use software solutions by Bruker to handle the often complex DART data. For targeted analysis, we can use TASK for multi-targeted screening and quantitation of DART and electrospray ionization data. This program IDs known compounds for data collection by both DART, again, and LCMS analysis, and from Bruker Mass Spec platforms ranging from triple quads to QTOF and timsTOF. Meaning you're really only needing to learn one piece of software for either analysis. So while this here we kind of have an extreme example of how complex DART data can get. So here we have 25 compounds identified from a toxicology standard with a 3-second DART analysis. So some analytes are going to stick out immediately to the naked eye, but it's easy to see how some of these analytes can kind of get lost in the spectrum. We're going chromatography free, so we're kind of seeing everything at once. So we're going to really use our software solutions to really kind of sift through this all. And TASK can help with that identification. So here we have the IDing of that drug mixture with, again, high confidence. So using our in-house database, we can quickly search through about 1,440 illicit drugs. So we're actually using our forensics database from our target screener solution. So if you were in this morning session, my colleague Richard went ahead and talked about target screener. So we're actually using that same database to sift through some of this DART data. And this database is updated on a yearly basis. So again, you can see how this can kind of help with the complexity of that DART data. So of course, we have accurate mass. So we can use that to help ID these analytes. Most of these analytes are matching with less than a 1 milladalton difference than the exact mass. And that's noted in this column kind of here. So this is in milladaltons. So most of these are, less than 1 milladalton difference from the measured value compared to the theoretical value. And it's no secret that one identification parameter that we lose with DART is retention time. We're trying to go chromatography free. So a few ways that we can help strengthen our confidence in library matches with high resolution mass spectrometry is one, through the use of isotopic patterns. And that's what this column is going to represent, this millisigma. So this is a scoring of how well the the experimental isotopic pattern matches the theoretical isotopic pattern of the given analyte. So the smaller the score, the smaller the value, the better the match. So again, we're seeing some great matches to the isotopic patterns. And another thing that we can obviously use is fragmentation patterns through MS/MS or broadband CID experiments. And as we're going to see in a moment, we can even have the ability to use collisional cross-section values measured with ion mobility. So with all those extra steps of identification criterion, we can help eliminate the need of retention times and help eliminate false positives. So what does this workflow look like as a whole? So to get your to go from sample to report, we kind of just have a quick 5-step workflow. So the first being is to pipette your samples onto that quick strip card. So often, quick and dirty dilutions are usually compatible to get your sample into the liquid phase. So we're usually kind of targeting a rough 1 ppm mixture. From there, we're going to place that card holder, so that card into the quick strip holder of the DART source. You're then going to generate your sample table to include any relevant information. This is similar to how you would set up, your LCMS injection table. Once that's all set, you're going to start your DART acquisition. And then from there, it's going to be just a couple seconds of ionization time per sample. And then once that's done, a sample report is going to be created automatically. And again, yes, these sample ports are created as soon as, can be set up to be created as soon as your sample analysis is done to populate reports with detected compounds. So this is, just one of the example of reports that we can generate. So this is going to provide you, kind of look at the report here on the left. This is going to provide you with the name of the identified analyte, the extracted ion chromatogram from that ionization event. We're going to get full scan and MS/MS spectra for the analyte, as well as MS/MS spectrum from the spectral library. So again, we can visually see, kind of how well the two are matching. So again, this allows you to go from clicking run on the DART source to getting a report in less than about 15 seconds per sample. And just as a reminder, you're always less than about 2 minutes away from switching back to your ESI source. So this is still giving you the ability to do your standard LC or UHPLC testing to help screen and identify your samples even further. So you're kind of getting, the best, the best of both worlds while still using the same software platform. All right, so now we're going to switch gears and talk a little bit about trapped ion mobility spectrometry. So I think the best way to introduce trapped ion mobility is through showing an example of its benefits. So here we have 3 sets of isomeric drug mixtures that have been ionized with DART and successfully separated with ion mobility. So again, here we have 3 sets of isomers. We have 6-acetylmorphine and naloxone, norhydrocodone and hydromorphone, norcodeine and morphine. So what we're looking at are mobilograms of this exact mass that's up here. And we can see we're getting separation between these 2 isomeric compounds. And the same goes for each of the sets. And then furthermore, with kind of our dual TIM cells, we can actually isolate isomers by mobility and perform respective MS-MS fragmentation. So here we're getting MS-MS fragmentation of a 6-acetylmorphine and naloxone separately. And again, the same goes for the other sets of isomers. So again, right off the bat, we can see some of the advantages that we can get with trapped ion mobility and how we can apply that to some samples that we may be seeing in the field. All right, so before we go any further, I want to review the fundamentals and make sure that we're kind of all on the same page with the terminology. So simply put, the collisional cross-section, or CCS, is a size of an ion and a measure of how often it'll collide with neutral molecules in a gas phase. So here we have 2 ions of the same molecular formula, therefore not distinguishable by mass. However, their different shape allows us to separate them by ion mobility. As a metaphor that we at Bruker like to use, we like to think of 2 sailing ships. So here on the right, we have 2 ships. So the more sails or greater collisional cross-section means stronger interaction with the wind or gas flow. So under the same conditions, we would expect that a ship with more sails to move faster than a ship with less sails. And the same goes with ions. So the larger the ion with greater collisional cross-section is going to interact more strongly with the gas around them, resulting in different mobility. So basically, with trapped ion mobility technique implemented in our Bruker timsTOF instruments, we can separate ions based on their shape and size. And better yet, we can accurately measure the CCS and use these values as an additional identification criterion. Now, to kind of get an even better understanding, let's talk about how TIMS actually occurs. So now trapped ion mobility spectrometry is first and foremost a separation technique within the gas phase. So this helps resolve sample complexity with an added dimension in separation. So increasing peak capacity and confidence in compound and characterization. Equally as important, the TIMS device also serves to accumulate and concentrate ions of a given mass and mobility. So enabling kind of a unique increase in sensitivity and speed along with additional dimensions of separation. So here we can see a kind of a diagram of a TIMS cell. So we're going to be having an electrical field going in one direction and a constant gas flow opposing that electrical field. So TIMS occurs actually in 2 phases. So the first phase is going to be to accumulate our ions. So here we can see we have ions kind of entering the TIMS cell. So these ions of larger size are actually going to migrate further into the TIMS cell before they get trapped by that electrical field. So now that we've accumulated and trapped our ions, the potential can now gradually be lowered. So ions are then released by decreasing CCS order. Controlling the electrical field ramp allows for controlling this elution profile. So we can see that as we kind of release them and decrease that electrical field, we get these to elute out and head to the mass analyzer. And now here's kind of an overall view of the timsTOF ion optics. And there's really just 3 key things that I wanted to point out. And that's going to be 1, kind of our orthogonal source design. So this is going to be the API of the mass spec. So this is where your ions are entering the system. So any kind of neutrals that happen to kind of slip past, the API, they're actually going to be just traveling straight through and not enter the TIM cell. So that's one way that we can help increase the robustness of the system. So the second thing I wanted to point out is kind of the position of the TIM cell. So notice that it's actually in front of our quads. So this actually allows for the ion mobility measurements of every ion entering the TIM stalk. And the last thing I wanted to point out is that we now have a dual TIM cell placement, meaning we have two TIM cells placed right next to each other. And this actually allows us to get a nearly 100% duty cycle. So to kind of bring it back to C's drug analysis, we can actually take a look at an example of two isobaric compounds that are co-eluting. We have tramadol and O-desmethylvenlafaxine. So while you may be able to kind of tweak your LC method and hopefully separate these two compounds further with either extending your elution time, you can actually use mobility to separate these analytes. So here we can see that at just a 5 square angstrom difference, we can actually achieve complete separation of these two isomers. So here we have tramadol and O-desmethylvenlafaxine. Taking a look at another example, here we have this group of PDE5 inhibitor analogs. So we can see that homosildenafil and vardenafil are actually co-eluting at kind of about 3.4 minutes. Again, you can try to tweak and lengthen your overall LC run, but using ion mobility, we can separate these two compounds, quite clearly. And it's impressive given the fact that the only difference between those two compounds is going to be that placement of that nitrogen. So with timstalk mass spectrometry, we've been able to analyze in kind of an analytical dimension. So we can analyze by retention time, accurate mass, MS fragmentation, and now ion mobility. So with the addition of ion mobility, we can get benefits to our analysis, like allowing for an additional criterion to ID these analytes. We have the ability to separate and quantitate isomeric compounds. And another benefit that I haven't quite shown yet is the ability to clean up chromatograms and spectra. And what I mean with that is something that we refer to as mobility filtering. So here we have an LCMS run looking at thiacloprid. So we see that with no mobility filter, our analyte is not being detected. And while the chromatogram may suggest that there's something there, it's possible that our analyte's kind of getting lost in the background. Since we have mobility data, we can start applying narrower mobility filters, meaning that we're looking at chromatograms not only of a specific mass, but also of a specific mobility. So this leaves us with kind of a cleaner and more distinct chromatograms. So what does this look like when we use the mobility information gathered to help clean up the mass spectra? So here we have a spectrum without any filtering. And again, if we filter by a specific mobility, we can extract mass spectra containing ions of that specific mobility window. So this can help isolate our analyte of interest to make sure we can see it clearly and kind of extract it from the background, or extract it from some of the smaller and less intense peaks. So to kind of compare this to something a little more familiar, this occurs similarly to how you would extract a spectra based off a specific retention time from like an LC chromatogram, but now with mobility information. Now, for kind of like the last chapter of today's event, I wanted to talk a bit about non-target analysis and coupling DART to other Bruker software solutions. And I figured what better way to demonstrate this with some authentic samples of forensic interest. So again, just to kind of quickly recap on TASK software, TASK supports various screening approaches and accurate quantitation when a calibration curve is available. So think compound identification with known analytes and databases, and preliminary identification, so kind of like suspect screening. So again, targeted workflows. So to work opposite of task, Bruker offers Metaboscape software for non-targeted workflows. Metaboscape uses statistical analysis to detect unexpected compounds and identifies known unknowns using public databases and spectral library searches. So some of the benefits to using Metaboscape is, again, of course, the non-targeted and semi-targeted analysis, but also the automated peak finding and data deconvolution for DART, ESI, QTOF, and as well as timsTOF data. So this is going to help generate a feature table of relevant ions detected within your sample. And it also has multiple annotation tools for unknown compounds, and also a set of built-in statistic tools. And now to demonstrate some of the capabilities, I have a couple experiments that I've been referring to. For experiment 1, we're actually looking at 3 different batches of similar sample type. So we're expecting to seeing similar active ingredients within each batch. So the goal for this study was to see if we can use DART mass spectrometry to distinguish one batch from the other. So this can help forensic practitioners determine patterns in seizures and help create trace samples to a point of origin. So 3 different batches with 10 vials each of dry product were sent to us in collaboration with CFSRE. And after a kind of a quick reconstitution and dilution with methanol, each vial was aliquoted out onto a quick strip card by just taking a 3 microliter droplet out of each vial. And this card was placed on our quick strip module, where we performed both full scan and MSMS experiments. So an example comparison of the DART data collected from different vials from different batches. So it's no surprise that just looking at the raw data, it's near impossible to determine if these samples are different at all. We are expecting to kind of see similar main analytes. So again, we have 337, which is going to be fentanyl. This 152, which is acetaminophen. That's no surprise that we're seeing them in all vials. But again, using kind of the non-targeted analysis that Metaboscape can provide, we're going to see if we can use kind of the statistic tools to kind of help sort through all this data and maybe help identify what we're not seeing. So using the information generated by Metaboscape, we can take that data and do some inter and intra-batch comparison to easily kind of take a look at it. So we can do statistical comparisons, and these are easily generated within the software, and do a kind of a 3D principal component analysis plot, which is demonstrated here on the right. So, again, out here we have the blanks kind of all by themselves, but when looking at batches 1, 2, and 3, we can kind of see that there's a distinct grouping within the batches. So this suggests that, yes, kind of at a bird's eye view, the spectra, the samples are all the same, but looking at different ion ratios, or maybe some of the smaller different analogs or precursors that are kind of buried in the lower level signal, we can use that information to be able to tell apart one batch from the next. And again, we can use these loading plots that we also get to begin to identify different features or ions and see how they differ from sample to sample. Now, while we will be able to identify, some relevant features, it is very likely that we won't be able to identify every feature. And that's okay, in this case, because, our goal in this experiment is that we're attempting to distinguish one batch from the next. But with, one of the benefits to Metaboscape is that regardless of feature identification, we can still see how they influence the loading plots and vary between batches. And what I mean is here, here we have this feature all the way out here, and that's going to be, this feature that's displayed up here. So this is actually going to be fentanyl. So to no surprise, we're seeing it in all our samples and not our blanks. But what we can see by looking at the box and whisker plots is, that the level or the intensity that which we're seeing fentanyl varies between, samples a bit, as well as, batch to batch. And the same goes for acetaminophen. While it doesn't vary as much from batch to batch, we can see that, there is a little bit of variation. And I just kind of point out, this feature all the way that's down here is whatever this 151 may be. While I wasn't able to successfully identify it, I can still see how the results from the experiment and how, the presence of this ion influences these loading plots. So again, we're not seeing anything in our blanks, but again, we can see that whatever this ion may be, it is, has a stronger presence in batch 2 than it does batch 1 or 3. But what if we do want to identify these features? So here we kind of have an example of a general workflow to go from raw data to feature identification, all within Metaboscape. So step 1 is actually going to be to, of course, acquire your data. So this is going to be for DART data, but again, this does work for ESI or LCMS data, and this handles both full scan or MS data. Step 2 is going to be doing our feature extraction. Now, this is an algorithm that you set up at the beginning, and then once that's all set, it takes care of all the data interpretation for you. So once you have your features extracted, you're then going to head and screen it against knowns or suspects using kind of a target list. So we always say we kind of start with target list and spectral libraries, because those are going to give you the greatest and quickest chance of identifying any of these features. But if that doesn't work, we do have additional tools that Metaboscape has built in to help identify these unknowns. And that's going to be step 4. So I'm going to kind of walk you through the process of this, step 4, to go from, the information that we've collected to go from feature identification. So the feature in question is whatever this compound may be at 281.1993. I wasn't able to get any matches within my target library or spectral library, so now I'm going to start with SMART formula. So as the name implies, this is going to be helping generating a formula based off 2 things, and that's going to be accurate mass and isotopic pattern. So SMART formula is about as smart as we let it be. So if you put 0 restrictions on it, it can generate hundreds, if not thousands, of possible formulas. But since we know a little bit about information, they're going to be, forensic samples. We know a little bit where we can put some restrictions. So right now, we have elements. We put restriction on what elements could be in the formulas to CHNOPS. And we also put a tolerance of 4 milladalton, so a relatively restricted tolerance, again, to kind of keep the amount of results low. If you want, you can add chlorines or bromines, or if you're working with fluorinated compounds, you can add fluorine to the mix. So again, you can customize this to however best suits your sample. So what we have down here is 6 possible formulas that it's generating, and it's going to rank these, of course, again, based on its accurate mass match between theoretical and experimental accurate mass, and of course the isotopic pattern. So I'm going to start with this first formula here, the C19H24N2. So what I'm going to do is take this formula, move it over to Compound Crawler, where it's going to do a structural or a formula search with online databases. So typically used are going to be, PubMed, ChemSpider, Chebby, but you can also use customizable user-generated databases as well. So again, this is going to be an online database or a database search based off this formula. And what we can see is, we have plenty of possible compounds detected. The nice thing about ChemSpider, it actually does pull reference counts. So that's a great indicator. So again, right off the bat, we see something of the imipramine that is 6,000 references. So that seems like a good match. But the second match is actually some type of fentanyl-containing compound. So again, given that I know we have fentanyl samples, this is also a very plausible match. So what I can do is actually take the top 10, 20, 30, 40 results and move them on to the next step, which is going to be METFRAG. So the top 10 compounds from Compound Crawler were now entered into MetFrag for in silico calculations. So these in silico fragments are calculated and matched with experimental MS peak list. So here we can see that these are all going to be fragmented in silico and scored against our experimental data. So we can see at the very top we have a score of 1 for this fentanyl compound, which when I looked it up, it's 4-ANPP, so that may be more familiar to some people. And then that imipramine that had a lot of references is actually only scoring down to 0.572. So again, this gives us nice confirmation that this is likely going to be that fentanyl-containing compound and not the one that had the most references. So once satisfied with our annotation, we can actually add this feature to our table. So furthermore, I can now add this analyte to an in-house target list, so the next time we run these samples, we can be sure to identify this compound again. So the idea is the more analytes you identify in Metaboscape helps speed up this process for future annotations. And kind of want to point out too that while it wasn't used in this specific study, Metaboscape also has a built-in CCS predict tool to help further identify analytes based off of ion mobility measurements. And I also want to reiterate, all these separate programs are built into Metaboscape, so you're not having to jump around between multiple software programs. It's all located very nicely and flows very intuitively within Metaboscape. So for the second experiment, we can actually take a look at adulterated paper sample extracts that were provided by our collaborators at the Institute of Forensic Medicine, Forensic Toxicology Medical Center at the University of Freiburg. So the samples in question are substances that are either sprayed onto paper or is completely soaked in drug solution and dried. Sometimes it's also a little more sophisticated, where they have actually double layered pictures or postcards with a kind of a small compartment containing the powders, which is where they're found. So it was reported that their local prisons, that the amount of samples actually went up and peaked at around 400 cases just in 2021. So this is kind of an inherent problem to some local correctional facilities. Compounds may vary from sender to sender and change over time as usual, but what they've kind of see in their trends is usually synthetic cannabinoids are the most common compounds found on these paper samples. Again, our trusty DART impact was used for a sample analysis. Samples were easily prepped with a methanol extraction procedure, and then shipped to our lab, where they were reconstituted with methanol and spotted onto our quick strip cards. Looking at this first paper sample, we're actually able to lengthen the ionization event of the DART, resulting in kind of a signal duration of 20 seconds. And what that actually allowed us to do was collect up to 200 MS spectra. And that's actually noted. So here we kind of have a full scan, and any one of these ions with kind of this red diamond notes that we do have MS information available. So using, again, full scan isotopic pattern and MS information, we're actually able to run that against some in-house libraries and determine that it's going to be for this MDMB, 4-EN Pinaca, and 5-fluoro MDMB pica detected within this paper sample. I also wanted to point out that besides Bruker libraries, non-Bruker libraries are also supported, as long as they're kind of in the right format. But this includes the NIST DART forensic database that was released back in 2021, as well as the Maurer, Meyer, Hepfer, Weber library, and of course many others. So this is kind of an open library concept where the user can actively grow and add analytes to these libraries as they wish. So now looking at another paper sample here, we actually shortened the DART ionization pulse back down to 3 seconds. So in comparison to the previous sample, the analysis time is now decreased by 85%. So in kind of a real world scenario where they're trying to analyze hundreds of cases, this is going to give them an even higher sample throughput. The obvious drawback being is now we're getting fewer MS spectra. So now we're down to about 40 MS scans, which in most cases, is going to be okay for seized goods, just as long as the number of compounds in one sample to be identified is usually small. So in certain cases, we're really just interested in kind of what is the illegal substance there. We're not really interested in all the binding agents or the active or inactive ingredients. So again, when running this through kind of our in-house library, we're able to generate a report detecting that this is also MDMB 4EN Pinaca. However, constantly new drugs are being synthesized, which I'm sure most of you are aware, and they're not always included in spectral libraries. So for example, we're looking at kind of a third paper sample here. We have an unknown compound at 331. So if a known compound is found, we can again apply that same kind of three-step workflow in Metaboscape to help identify it. So again, we're going to start off with using SMART formula. This first result here again has good good mass agreement and then also good isotopic pattern agreement with a very low millisigma result. So again, we're going to use this value and move forward with compound crawler. So right off the bat, what we're seeing is, of course, some suspected synthetic cannabinoids. So that is reassuring that we're on the right track. And then we could take those first 40 structural candidates from compound crawler and subject those again to in silico fragmentation. So the top hit, the one with a score of 1, is coming back as with a synthetic cannabinoid of ADB butanaka. And the second and third top are actually another synthetic cannabinoid called AB pinaca, which differs from that ADB butanaka with a location of 1 methyl group. So again, if we want to, we can stop here, say it's ADB butanaka, and move on. This is kind of a way that we can do kind of a like standard free testing, is using kind of this information available and generate some of these results. However, looking at this agreement or the scoring, we get a score of 1 and a score of 0.843. So if those are a little bit too close to comfort for you, you can of course always go out and purchase some reference standards, which is what we did. We purchased reference standards for both of those synthetic cannabinoids. We analyzed them with, and collected MS information with DART to make sure we're kind of getting the highest level of certainty. And then we added that MS spectra to the library and researched the paper samples against it. So now, without a shadow of a doubt, we're getting an excellent match with ADB butanaka. And kind of the one unique fragment between the two is going to be this 201 and then the 215 in the AB pinaca. So again, looking at, visually looking at this AB pinaca, we can, exclude that now without hesitation. And now we have these two compounds in our library. So in general, libraries can, easily be expanded by the user with new compounds, and, you can add to these libraries with very minimal effort. So to kind of wrap up, the workshop today, we talked about chromatography-free DART and high resolution mass spectrometry and how they pair well and can offer both the, kind of the accuracy and throughput that's required for targeted analysis of seized drug samples. With the addition of ion mobility with our timsTOF systems, we can actually offer an additional analytical dimension of measurement with both the addition of CCS values and the ability to separate isomers. Powerful non-targeted software such as Metaboscape can easily identify ions of significant value with samples, and actually comes equipped with tools to statistically compare samples and help identify unknowns. And DART-QTOF analysis with authentic forensic samples demonstrated the versatility of the ionization source and the speed at which the samples can be analyzed and identified. And I just wanted to leave you off today with just kind of a brief overview of our mass spectrometry product portfolio. While I only did talk about the items I've circled here, a couple different high resolution mass spectrometers and a couple pieces of software. We do have different options for triple quads, GCs, as well as a nice state-of-the-art MALDI systems, as well as kind of the extreme resolution option for MRMS. So if you do have any if you do want any other information about those systems, feel free to reach out. We'd be more than happy to talk with you all. And then one thing I wanted to mention, I'd be remiss if I didn't say anything about it, was actually our new and latest instrument coming out of the Applied Markets Group, and that's going to be the Evoke DART TQ Plus Mass Spectrometer. This is going to be featuring the first fully integrated DART source. So if you remember, we had that blue cylinder kind of on the front of our QTOF. We now have this integrated, integrated DART source that's a little bit smaller and can switch even quicker back from DART to ESI. And not only are we featuring this new integrated DART source, we actually made some significant improvements to our triple quad with we're able to do more MRMs per second and have been able to increase the scan rate. So yeah, we're very excited to have that rolling out, and can't wait to start seeing it in action. So of course, I'd like to acknowledge both CFSRE and the University of Freiburg for their collaborations with these samples, and I'd like to thank you all for giving me your afternoon and listening to our workshop. So thank you all.
Thank you so much, William. Thank you for that great presentation, really engaging. Before I go into the Q&A, I just wanted to make a note. I know a few of you were having some technical difficulties with your audio. If that was the case, the recording will be available to all who attended after the fact, so you won't be missed out in that regard. All right, so let's get into the fun stuff. Let's look at some of these questions. All right, William, it looked like methamphetamine and phentermine were identified in the same peak. How does the system do when analyzing isomers?
So I believe, let me see if I can kind of quickly jump back to this slide. It was a little bit before that. Yes, so I believe it was kind of in this scenario we're seeing, the methamphetamine and phentermine. So in this scenario, unfortunately, we are just using our QTOF system, so there's no ion mobility information present. So with that being said, I'm not too sure what the fragmentation patterns of phentermine and methamphetamine are, if they differ. But if they are different, then we have that available, so where you can do some MS experiments to see what fragments are present. But in this case, we're kind of left with the ambiguity of what's what. So unfortunately, with our QTOF system alone, it's just, we see this peak of accurate mass. We know it's going to either be methamphetamine or phentermine. Further experiments, we can hopefully isolate it a little bit further. Again, but this is kind of makes a good case scenario for possibly using timsTOF to help exploit, and separate those two isomers.
Thank you. Can you optimize the ion mobility separation by changing the voltage or gas pressure? If so, will that change the CCS? Do you have trapping capacity issues when you inject many ions?
Yeah, so you can optimize the mobility separation. So you can actually adjust the kind of the window in which you're separating or you're collecting or trapping these ions. So if you want kind of a much narrower window, you can get usually a little bit better resolution. So the gas pressure is going to you can alter it to kind of change the field, but that's going to remain constant during the actual analysis. And the way we can kind of get by with correcting it is, again, just using a kind of a tune mix to make sure that we calibrate whatever settings we change. We calibrate it back to a tune mix, and then since we know the CCS values of our tune mix, we then can scale, the data we get appropriately. And then I think the second part was, do you have any capacity issues?
I think capacity issues when you inject many ions.
So I believe that the software can help correct for that. So, we're kind of, it is kind of monitoring to make sure. I'm probably not the best person to speak on that. So if you like, I can certainly follow up, with a more detailed explanation, just to make sure I'm not, saying anything that is incorrect, but I'll definitely mark
Thank
that
you.
and we can follow up.
Sure. You mentioned that either helium or nitrogen can be used as the ionization gas. Are there any benefits to using one over the other?
Yeah, so traditionally, there's been numerous amounts of literature using helium as the ionization gas. And then when comparing between helium and nitrogen, we found that we typically see kind of a more efficient ionization with helium over nitrogen. And we typically see kind of a reduced background with helium over nitrogen. And I know kind of some of the main concerns with being obviously, the prices of helium, the shortages, but with kind of our latest kind of advancement with DART, which I think was back in 2020, we've now been able to kind of time the ionization process a little more efficiently, to where now we're only using helium when there's a sample in front of the source. So we're seeing, about a 95% of helium conservation. But what I also like to say is, nitrogen will work. So if you're trying to do kind of some method development or just testing to see if something will work, starting with nitrogen is a very easy place to start. We use nitrogen as a standby gas, so that's already going to be, present. So you can easily toggle between helium and nitrogen and kind of see what works best for your sample.
Thank you. And I think we have time for one more. What are the limitations on sample types? For example, are these instruments appropriate for use on plant material, such as marijuana or mushrooms?
Yeah, so actually, I actually collected some data of recreational marijuana products, and was able to directly kind of probe, some of the flower and analyze those directly right off of a glass capillary. So again, that's gonna be a great use scenario for QTOFs. And other plant materials, I know some of our colleagues in Bremen have actually been looking, while this may not be relevant for forensics, but have been analyzing truffles with DART and using high resolution mass spectrometry. So again, we kind of have a plant material that they're analyzing. So in some cases, you can directly kind of probe the raw material. However, you may be needing to do just kind of a quick extract, as we kind of did with like the papers, where we're just doing a quick extract of methanol, just to make them a little bit more easier to handle. So yeah, they're definitely, I would say definitely appropriate.
Options. Really fascinating stuff. So we do have a few more questions. I don't think we'll get to all of them today. So we do get all of your questions given back to us from the organizers. We will reach out to all of you where we didn't have time to answer them. And if you think of a question that maybe didn't come to you during this recording, please feel free to reach out to us. Our contact information is available through the symposium. I would like to thank everybody once again for your time today, and especially to our presenter, William Fatigante, for his time. Great presentation, William. And I think everyone should have a beautiful day. And thank you again for your time.
Thank you, everyone.